In this video, we're going to learn how the second derivative of a function affects the graph of that function, and then we're going to work three common types of examples concerning the second derivative and the curvature of a function. So in the picture on the left, I've shown an example of what we call concave up or upward curvature in a function, and then in the picture on the right, we have concave down or downward curvature of a function. Notice that a function can be either increasing or decreasing as it curves upward. So in the left picture, on the left section of that curve, the function itself is decreasing basically on the first half of this curve, and then the function itself is increasing on the second half, while the entire time it has the same upward concavity or upward curvature. And the same is true for downward concavity. I can have a function that's going up or increasing as it curves down, or I can have a function going down as it curves down. And that's what this function is doing on its left and right sides. So how can derivatives tell us about concavity? Let's look at a tangent line to the first curve as we move left to right along the graph. We start with slopes that are large and negative, and then the slope gets shallower, but still negative. So those are smaller negative slope values. Then at the bottom of the valley here, the slope appears to be 0, and then small and positive slope, and finally large and positive slope. So what's going on here is that the first derivative is increasing its value the entire time. So an increasing slope is the same thing as upward concavity. Similarly, in our concave down picture, we start with a large positive slope, and then that positive slope gets smaller, but still positive. Then we hit a slope of 0 at the local maximum there. Then we get a small and negative slope, and then a larger and negative slope. So this time, the first derivative, or the slope value, is decreasing the whole time. It had large positive values and then consistently decreased until it had large negative values. So a decreasing slope gives us this downward curvature or downward concavity. So we arrive at a reasonable definition of concave up and concave down curvature. And there it is. We just say f of x is concave up if f prime of x is increasing, and concave down if f prime of x is decreasing. But it's important to remember qualitatively what that curvature looks like. We can refer to concave up as upward curvature and concave down as downward curvature. But instead of looking at concavity in terms of changes in the first derivative, we can reformulate this statement in terms of the second derivative. We recall that when a function is increasing, that means its derivative is positive, and I'll post a link to the video where that idea was first introduced. So if the derivative is increasing, then the derivative of the derivative is positive. In other words, we get upward concavity if the second derivative of f is greater than 0, and downward concavity if the second derivative of f is less than 0. Again, just to practice this idea, if I look at the case of concave down, saying that f double prime is less than 0 means the derivative of f prime is less than 0, which means f prime is decreasing, which means we have downward concavity. So now we have a second derivative test for upward and downward concavity. Now the final thing I want to add to this slide is that a point of transition between upward and downward concavity has a special name. And these points where the concavity switches are called inflection points. So in our definition, we're saying if f of x is continuous at x equals a, and the concavity changes direction at a, then a is called an inflection point of the curve. So we know we have concave up behavior if the second derivative is positive, concave down if the second derivative is negative. So naturally, we're going to look for inflection points where the second derivative is equal to 0. But then we have to be careful to check to the left and right of those candidate points to make sure the sign of the second derivative is actually switching at that point. If you can show that the second derivative changes sign, then you know you have an inflection point. So now we're ready to look at a few common types of examples with concavity and inflection points. So in our first example, we're given a graph of f of x itself, and we're asked to approximate the values for the intervals of increasing and decreasing and concave up and concave down. So just looking at a graph and approximating these things, we're going to get fairly crude approximations, but we're just trying to highlight some of the qualitative features of this graph. So we'll start with increasing and decreasing. And this is a bit of a review question. So increasing means the curve is going up as we go from left to right. So it looks like this thing just runs off to negative infinity. We'll just assume that is defined all the way to the left. And we'll say this function is increasing from negative infinity all the way to the top of this hill where I have a local maximum. Well, the top of that hill doesn't look like it occurs at an integer. It looks like it's something like negative 1.8. And most textbooks will state these intervals of increasing and decreasing as open intervals, even though closing the right end of this thing would still satisfy the definition of increasing. All right, and then we have another interval where this function is increasing, so I'll put my union sign in here. And it looks like f of x starts increasing again right around here, which looks like about 1.3. So from 1.3, and then it continues to increase off to infinity. So f of x is decreasing in between those 2 points that I already marked. So that's from negative 1.8 to positive 1.3. Again, just making crude approximations by looking at the graph here. So what about concavity? When I look at the graph of f, I see downward curvature happening all the way along here, almost to about right at the origin. It's kind of hard to tell if that's actually the inflection point, but there is an inflection point in there somewhere. And then I switch to upward curvature to the right of that. So the curvature is downward concavity from what appears to be negative infinity all the way to about 0. We'll just go ahead and say that it turns out that nice. We're going to put the inflection point right at 0. Then I switch to upward concavity, and that's going on from 0 to positive infinity. So downward curvature on the left side of the graph, upward curvature on the right side of the graph, and an inflection point sitting at x equals 0. Our second example is a little bit more tricky. This time we're given a graph of f prime of x, and we're trying to find the intervals of increasing, decreasing, concave up, and concave down for the original function f of x. So now I need to think of increasing, decreasing, concave up, concave down in terms of the behavior of f prime, because that's the graph that I have. So remember, a function is increasing if its derivative is positive. So I just look for where this graph is positive, in other words, above the x-axis, and that looks like the interval negative 2 to 2. And we remember that a function is decreasing if its first derivative is negative, which appears to be happening on negative infinity to negative 2. I'm just looking for the value of the derivative to be negative. In other words, this graph is below the x-axis, and we put that together with the interval 2 to infinity. So that's where the original function f of x is increasing and decreasing. So what about concavity? Remember, we're not talking about the concavity of the graph we're looking at. We're talking about the concavity of the original function f of x, and we're given the graph of its first derivative. So it's most useful to think about concavity in terms of the behavior of f prime here. And remember, concave up means f prime is increasing. And I can see that this function is increasing from negative infinity up to this local maximum of f prime here. That looks like it occurs at basically negative 1/2. So f prime is increasing, and the original function f of x will be concave up on negative infinity to about negative 0.5. Now I look for where the first derivative is decreasing, because that'll give me downward curvature in my original function f of x. And f prime appears to be decreasing on the interval negative 0.5 all the way to infinity. And again, that point where we switch from upward concavity to downward concavity, that's the location of an inflection point in the graph of f of x. Finally, we get an analytic example where we're just given a formula for a cubic function, and we're trying to find everything this time. So we're reviewing everything we know about increasing, decreasing, local extrema, intervals of concavity, upward and downward, and the locations of any inflection points. So we start this out by studying the first derivative of the function. So that's going to give me a 6x squared plus 6x minus 36. And we're interested in where that first derivative is equal to 0. That allows us to quickly find the intervals on which my function is increasing and decreasing. And just a reminder, the solutions to this are called the critical points for our function. So I can factor a 6 out of this, or I could just divide it out. I think it's a little more useful to factor it out, and I'll explain why in a moment. Okay, and then we're going to factor that quadratic trinomial, and that factors into an x plus 3 and an x minus 2, and we get our solutions. X is equal to negative 3, and x is equal to positive 2. So those are the two values of x for which the derivative vanishes. Those are the critical points, in other words, the candidates for local extrema. But we also want to map out the sign of the first derivative in all the other regions on the number line. So let's say negative 3 is right here on our number line and positive 2 is right here. And then we start sign testing in these three regions of the number line. So I'm thinking, what if x is to the left of negative 3? And again, it's useful to have this factored form of the first derivative. Just a reminder, that expression on the left side of that equation is just the first derivative itself, and we were setting it equal to 0. So there's the factored form of the first derivative. If x is to the left of -3, that makes this first factor negative. The second factor is also clearly negative because I'm just subtracting 2 from it. So negative times negative is a positive, so f prime, I'll just go ahead and mark this number line as an f prime number line. F prime is going to be positive to the left of -3. Now in between -3 and 2, x plus 3 switches signs. That becomes positive because I'm adding 3 to something that's bigger than -3. My second term, I'm subtracting 2 from it, but in this region, I'm talking about numbers that are less than 2, so that one's going to come out negative. So I have a positive times negative, which gives me a negative result. Now you might be more comfortable just subbing in an explicit test point if you want. You could throw the number 1 in there or 0 or whatever you're most comfortable with. Notice that if I replace x with 0, I get 3 times -2 here, which gives me a negative result, and it agrees with the previous analysis. Now to the right of 2, x minus 2 clearly becomes positive, x plus 3 is positive, and a positive times a positive is positive. So we have our regions now of increasing and decreasing, and we can also identify the local extrema. So our increasing intervals, again, we'll just use open intervals for this. That's -infinity to -3 together with 2 to infinity because the first derivative is positive, so we'll see the function going up. Our intervals of decrease, that's -3 to 2. And mercifully, all we've been asked for in this problem concerning the local extrema is their locations. So we don't have to find the y coordinates that go with these x coordinates. All I have to do is write down the x value corresponding to my local maximum, local minimum. So when I switch from increasing to decreasing, that's a local maximum. And I'll post a link to the video where local extrema were first hashed out. So I get a local max at x equals -3. And then when I switch from decreasing to increasing, that's a local minimum or the bottom of a valley, and this occurs at x equals 2. So that's kind of just the first half of the problem, because now we have to get into studying the second derivative of this function. And that's going to allow us to answer questions about concavity and inflection points. So that's the next piece, f double prime of x. I'm going to go back to this expanded form of f prime to make this easy. And when I take the derivative, I get 12x plus 6, which then factors into 6 times the quantity 2x plus 1. So setting the second derivative equal to 0, we'll be able to find candidates for inflection points and then do sign testing to the left and right of those solutions to figure out the sign of f double prime and therefore the concavity. So what I want to do is solve 6 times the quantity 2x plus 1 is equal to 0. And of course, the 6 doesn't matter there. I subtract 1 from both sides and divide by 2, and I find that x is equal to -1/2. So this is a candidate for an inflection point, but we have to show that f double prime changes signs left and right of that in order for us to be sure. So we only have one of these guys. It's at -1/2, and then I need to test the sign of f double prime to the left of this point and the right of it. Again, you can sub in explicit test points if you're more comfortable doing it that way. Like I could sub in x equals -1. That gives me a -1 in the parentheses here, and f double prime is negative. Or I can think more abstractly about it and just say, okay, I have an x value less than -1/2. When I multiply that by a 2, I end up with 2x being less than -1, and when I add 1 to it, the result is negative. To the right of -1/2, again, I could use an explicit test point like x equals 0, and that would give me a 1 in those parentheses, and therefore a 6 for f double prime, and it's positive. Or I could just say if x is bigger than -1/2, and then I multiply it by 2, I get a number that's bigger than -1. So in these parentheses, it's positive, and f double prime is positive. So apparently at x equals -1/2, we have an inflection point. So I'll just label it right here. That's an inflection point because I see a sign change in the second derivative. To the left of that, I have a negative second derivative. Again, that means f prime is decreasing, and it means we have downward concavity. So my original function is concave down on -infinity to -1/2, and concave up on -1/2 to infinity. All right, so now it's the moment of truth. We can bring in a picture of this function. And this function has really huge y values, so I had to rescale it vertically to fit it on a reasonable graph. So all the features are at the same values of x, but I've squished the graph vertically just to fit it into the picture. And let's see if everything works out here. Our original function was supposed to be increasing on negative infinity to negative 3. Well, here's negative 3. So this looks good. Negative infinity to negative 3. I see the function going up as I go to the right. Together with 2 to infinity. So that looks good too. The function's going up on that interval. And then in between on the interval negative 3 to 2, I see the function going down. So all that stuff is working out. And of course, that corresponds to a local maximum at negative 3 and a local minimum at 2 when I switch between increasing and decreasing and vice versa. Then my inflection point is supposed to occur at x equals negative 1/2. So right here. And these are a little bit hard to estimate visually. I'm really just saying, is it plausible that this is the point where I switch from curving down to curving up? And it looks pretty good. And again, that left section to the left of negative 1/2, that is downward curvature. I see a derivative that's decreasing there. And then to the right of negative 1/2, to the right of negative 1/2, I have upward curvature and it's concave up on that interval. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.